Okay, guys, so let's go. Okay. So let me show you my screen and you tell me if you see my white screen. Do you have it? Perfect. Okay, so today, guys, we're going to talk about polynomials and the use of polynomials. Believe me, it's very strong in economics and finance. Okay, so let's start with very basic stuff. For example, I have 3x cubed plus 2x squared plus x minus 5, and this is equal to 0. Do you remember this type of polynomials? And one of the first things that you want to do, guys, for example, is to find what are the values of x that satisfy this equation. When we do optimization, we do this type of things, we always try to find values of x in a given equation. Got it? This is also the equation for the internal rate of return. Do you remember that we have been working? The internal rate of return is the interest rate that makes the net present value equal 0, for example, something like that. Now, first of all, how MATLAB understands a polynomial. So a polynomial, this polynomial for MATLAB is going to be, let's call this P. The way MATLAB is going to understand this one here is simply you write this one. So for MATLAB, this is power 0, 1, 2, and 3. Got it? So that's the way MATLAB reads. So you need to be very careful when entering a correct polynomial. Let's say, guys, that you have a 4x squared plus 3. How do you enter this polynomial?
You would
Is it 0
Yeah,
or 0, 3?
that's right. So 4, 0, 3, like that?
No, the first one is 0, and then 4, and then 0, and then 3.
Oh, no, no, no. Yeah, you're comparing with this one here. Yes. No, no, but this is an independent equation, an independent polynomial. If it's
Okay.
an independent polynomial, yeah, it should be 4x squared plus 3. So it should be 4. This is going to be power 0, power 1. There is no power 1 here. And 4 power 2. Make sense?
That makes sense.
Okay. So one of the easy thing to find are the roots. So let's find the roots of a polynomial. Let's write the first one here, guys. Create P. 3, 2, 1 minus 5. Let's create P. So P is going to be 3, 2, 1 minus 5. So this is going to be my polynomial. Okay, let's call R. If you want to find the roots of the polynomial, you want to find what is the value of x that satisfies this equation, the command is roots. Now, the other process, the inverse process, guys, is once you find the values of x, if I give you the values of x, you should be able to recover the equation, correct? Okay, so how do we do that? So let's call this PP equals poly, so that the MATLAB command is poly of the roots. Now, why do I have, apparently I have different values here. So what MATLAB does, guys, is normally what we do in econometrics also, guys. It standardizes the value respect to the first value. So indeed what it does is everything divided by 3. So if you do PP times 3, here you go with your value. Okay, so this is a funny way, guys, of presenting in econometrics for those of you that took econometrics in the past. Do you remember that when we did the eigenvalues and all this stuff, always everything is standardized respect to the first variable? Make sense? Now, of course, what we need to do is we can sum. Where's my mouse? So if I want to sum two matrices, guys, two polynomials, how do I do that? Can I sum 3x squared plus 2x squared plus x minus 5? Can I sum p plus p1? Can I do that?
Yes, you can.
Yeah, I can, but I need to do something. Because remember, how do you sum these two guys? If you sum these ones here, remember that the rule, if you do this by hand, is going to be, no, this is too small. I think is this too early? Let's see if this works. Plus 2x plus x minus 5. If I want to sum this, I will do, sorry, this is 2x squared. What I do is simply is 4x squared plus 3. Do you agree? And then you simply sum. So this is going to be 3x cubed plus 6x squared plus x minus 2. You remember that? So that's the rule. So how do we tell MATLAB that they need to do this stuff? Well, we need to pad the numbers with zeros, correct? So I need to do a P1. This is what you were saying, Bafana. So let's complete this one here. So I will do what was my other one? Let's call P1 was equal to, the original one was 4, 0, where's this one? 403. Okay, but I cannot sum P with P1 like that. So what I need to do, guys, is I can call P1. It's going to be, it was 0. It has power. What is P1? P1 is 1, 2, 3. Power 3. Okay, so power 3, 1, 0. So this should do it, right? Power 3, 2, 1, and 0. And P equals 3, 2, 1, and 0. So now I can sum. I can do P plus P1, for example. And then we got the result is 3x cubed, 6x squared plus x minus 2. Make sense, guys? Okay, so let's define a couple of matrices. Let's define A. Let's do, something simple. And let's define B. What is my, just two matrices. The way you multiply matrices, guys, is simply, in this case, is let's call this M. M is going to be the MATLAB command for multiplication is convolution. Convolution of A and B. So what is this one? How do you read this one, this polynomial, guys?
Oh,
So it should be what?
to the sixth power?
Yeah, it should be x to the 6. It was 1 second. 0, 1, 2, 3, 4, 5, 6, right? Is x to the 6 plus 6 to the x5 plus 20 x4 plus 50 x3, etc. Makes sense to you? So that's the way you read the polynomial, guys, the result that MATLAB has provided to you. Now, I think in your file, in your Word document, what is the first thing I sent you? Yeah, can you copy this function here, analyze this function in a couple of minutes and see how this works? So copy this one here in MATLAB, is polyadd. Let me open polyadd here. Okay, analyze the program in a couple of minutes and understand what we're doing and why we are doing this stuff. And let's use, guys, A. So let's use as a test in these two. So you want to add these two ones here first. Okay, 1 minute, guys. Ready? You understand? Okay, basically, I need to run this program from a command window because I have input arguments A and B, and I have a P that is going to be the resulting polynomial. So the program, what it does is simply sums. Okay, so what this one does is simply, it requires two arguments. Number of arguments must be 2. So if I enter only one argument, I will have an error, not enough input arguments. Agree? So this is this part here. Now, in the second part, what I'm doing is I'm making everything as a row vector. Sometimes I can enter a column vector. So what you do here is you simply always shift it as a row. So let's explore this one here. So we run this one. Take a look to A. Well, A is a row vector, but what this is doing, guys? This one here, guys, is a way to transform anything that is a row. If it's a row, it will stay a row. If it's a column, it will move it as a column. Got it? So this is one trick to do that. Is A, everything that it has, simply transform it into a row. Well, in this case, we don't have anything. I have A, well, I have B. And then what I'm doing is I need to be sure about the dimensions of the vectors, correct? Because if the dimensions don't match, I need to do something. Got it? Good. So what we expect is that the individual that has entered the polynomials, he knows the rules of the polynomials, okay? So what we do is the following. NA is 4 and NB is 4. In this case, I don't need to do anything, right? This is the way to remember this matrix, guys, the zeros. It creates only zeros. What dimension? What is going to be one row? And n minus b. So if n minus b are different and nb is larger than na, this is going to be a positive number. Agree? Let's assume that nb is 4 and na is 3. So it's going to be zeros, one row, 4 minus 3, 1. So it's going to be 1, 0. Make sense? Now, what happens if NB is smaller than NA? This is going to be a negative number, correct? You cannot, the index of a matrix never can be a negative number. So, for example, where's the position of A minus 1? It doesn't exist. It's empty. So basically, when NB is smaller than NA, this part here is going to disappear, and this one is going to stay like it is, because it's supposed that this one has the longest dimension. Make sense? And this does exactly the same. If needed, it will put zeros in front of that. In this case, we don't need it, so we simply run. So let me run this stuff. And I have here my P. Got it? Now, guys, can you test your sum? Do you remember we have created this matrix M? This matrix M is 1, 2, 3, 4, 5, 6, 7. So it's power 6, correct? I want to sum M with A. So I want to use my polyad. But now I said A with M. Can you do that? Can you do the test and check what happens in here? So run this one here and analyze your model. Allow me to see. Yeah. Runs. So let's continue. Here we have an issue. Do you see? N of A is 4 and N of B is 7. Correct? So which one needs to be paired with zeros? This one here. It's going to be 7 minus 4, 3. So it will put 3 zeros in front of A. Make sense or not, guys? And then it simply runs. So we can run this one here. And here we go, guys. Make sense to everyone? Okay, this padding, these small tricks, guys, is going to make your life very simple later. Okay. Now, before I forget, guys, so I will send you perhaps early tomorrow. I'm not sure the symbolic mathematics, and then I will send you guys a lot of programs. Seriously, it's going to be a lot of programs. And what I want at the end of today is that you send me. We need to work in. How many are we? Give me 1 second. All right, I need to see. Let me stop sharing just to see how many we are. Yeah, we are 8. So I want to work in groups of 2. So you need to join in groups of 2. Got it? And I will give you specific programs that you need to read, understand, and you're going to be presenting this on Monday. So like me, you open your file, and then you're going to explain what this program is doing, line by line, run line by line, and show me what the program does. Make sense to you? Okay, so it's going to be one very long program and a couple of small programs that use a lot of symbolic mathematics, so I want you to understand. So it's going to be done in groups of 2. Of course, you can divide the work. It doesn't matter. You can work in Zoom. But on Monday, guys, you're going to start presenting what you have been reading and how the model works, etc., etc., etc. Make sense? Okay?
Yes, Prof.
Perfect. So let's continue then. There is another program that I sent you guys. Can you please upload that and create your M file? Is this one here? Polyad 1, copy all this one here. Again, 2 minutes, read, understand, and what's going on there. Okay, 3 minutes, and then we continue. Let me stop the recording. Please remind me to continue. Yeah, so let's review very quickly. So what this is doing, guys, is simply checking the number of arguments that we have. If we have two arguments, it simply uses the polyad that we have used before, this one, only once, and simply gives you the p dot, the sum of these two vectors, sorry, polynomials. Otherwise, if we have three, what it does is it simply does one by one. So P1 is going to be first the sum of A and B. This is stored at P1, and then P1 enters as the argument of the same vector that we have done, and then you compute your P dot. Make sense? And you can do this later, more flexible, guys. You can have as many arguments as you want. This is going to be an assignment. Make sense to you guys? Clear?
Yes.
Perfect. Okay, so we can continue working on something that is really important, guys, is derivatives. We use derivatives in economics quite a lot, right? So how derivatives work? So remember, guys, imagine that I have f of x equals 3x squared plus 4x plus 2. So derivative of f of x respect to x is going to be simply 6x plus 4. Do you remember that? Very common stuff. Okay, can you make this in MATLAB? The MATLAB command for this one here is called polyder. Poly derivative. And of your vector, of your polynomial. I don't know how do we call it. Let's call it Q. It is 342. You agree? So let's call this QD equals polyvar of Q. Oh, why it doesn't recognize? Not polyvar, polyder. Make sense to you? So x squared is 2 times 3. This is 6x plus 4. Make sense to you? Yep.
Yes,
Another
Prof.
thing that we need a lot, guys, is imagine I give you a function. Now, let's assume this function here, okay? Well, let's assume I give you a function like this. Where is my mouse? Here we go. Derivatives. Function evaluation. So, for example, guys, we have the following equation. So we have x cubed plus 4x squared minus 10x minus 10. And I tell you guys, I want to see the graph of this one, or I want you to evaluate these values in a given interval. Okay, so evaluate this one here. Let's say in the interval -1 and 3. That's common, right? If you have a line equation, you have a polynomial, you have whatever. So how do we evaluate that? The MATLAB command is going to be polyval. And you're going to see how powerful is this one here. So let me write this first in map. Let's call this a P, okay? So my polynomial, let's call the polynomial representation of this one here, let's call it P. 4, 7 minus 10. So P is going to be equal to 4, 7. No, what was that?
1,
1, 4.
yes, -7,
Yeah,
-10.
-10. So this is my polynomial. Do you agree? And then I want to evaluate this one here. We said in what? Okay, we can create lean space. Do you remember that? -1 to 3. So remember, guys, lean space, it is from here to here, how many variables? When you do that, when you don't write a third variable, it implies 100 of observations. So the default is going to be 100. So x is going to be from -1 to 3. How many variables, how many values in between? 100. Make sense? And then we can evaluate this one here. So let's do y equals polyval. What is my polynomial? P, and in what range? X. Okay, better if we see this as a plot. So we can do a plot of x, y. Very simple plot. We can do some titles. What do you want to call it? Perhaps we can call it polynomial. Makes sense? So we can do x labels. We can call it x. And we can call y label, let's say y, for example. You see? An easy way of evaluating functions, guys. And this is very important when you do macro, micro, or any other thing when they give you functions. And I remember when I was in school, I had no idea how the function looked like. Really, of course, I know the quadratic, the cube, you have some, but you don't have that clear idea. Do I have a maximum? Do I have a minimum? I have no idea. Got it? Easy. Just create the range, the polynomial, evaluate the polynomial, plot it. So you can have it a beautiful way of seeing what you're doing. Make sense to you now, guys? Up to now? Roots, poly there, polyval, and basically those are the ones. Okay, now, let's talk a little about curve fitting and interpolation. So let me share my screen again. So what is the difference between curve fitting versus interpolation? So let me move to here. Versus interpolation. Okay, so imagine, guys, that I have the following data. Okay, I have my x, have my y, and imagine these are the values that I have. Okay, so these are real values, observations. So when you do curve fitting, guys, is you try to use a mathematical tool to fit as best as you can your data. So OLS, for example, is one technique. You try to minimize the sum of the square of the errors. Do you agree? There are techniques that you minimize the norm, etc. But fitting means simply trying to find a line or a function that best describes this data. So, for example, if the best fit for this one here, perhaps is something like, let's say something like that. Do you agree? Now, what is interpolation? Well, interpolation is completely different, guys. Interpolation is simply trying to understand what can happen in between two observations. Got it? Then, basically, if we take these two values here, this one here and this one here. So what the interpolation is going to try to do is going to try to see what is the most likely value happening here, what is the most likely value happening here, what is the most likely value happening here, etc. Got it? And this looks very robotic, do you agree? It looks line, 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 line. So there is something that is called an spline or cubic interpolation. A spline or what is called cubic interpolation. So what it tries to do is tries to not make it very robotic, but tries to find a kind of a curve, a cubic function between these 2 points. So basically, guys, when you're going to see the cubic interpolation, it's going to look more like something like that looks like that, okay? It is not assuming that everything is linear, but it assumes that there is some gravity going on, so it's more like a curve, okay? We're going to see that in a minute. Makes sense to you? So when you talk about curve fitting, it's basically you're trying to find a model in such a way that your best fit model, satisfies certain condition. And interpolation is basically you try to find and use the data to see what is the most likely value between two of them. Make sense to you guys? Okay, so I send you, what is this? Let me put this on here. What is MATLAB? I send you guys, let me close this one here. MATLAB. And I send you, yeah, can we copy these two? So I have the data X and Y. Okay, so let's define n equals 2. And what is 2, 3, 1? Is basically if it's 1, it's linear, quadratic, cube, etc. So what we're going to try to do first is fit. Okay, so let's call P equals polyfit. So this is the MATLAB command. By the way, this is also, if you do 1, this one here is the OLS model. Huh? Okay.
Sorry, if
Polyfit
you do one where?
in here. So n is going to be the polynomial degree.
Oh, okay. If
I
n
will
equals
show you in a
one.
minute.
If n
Yeah.
equals one. Okay,
Yeah,
yeah.
yeah, exactly. So let's do a polyfit between X and Y. This looks like an scatter, and I want the fit to be degree 2. Got it? So what we are doing here, guys, is trying to find an equation that best fit the data. Got it? So basically what this one here is telling to you, you know what? The polynomial that best fits this data is this one here. Minus 9.81, 21. So this is minus 9x squared plus 20x minus 0.03. Got it? Okay, guys, can you plot this function? So let's plot this function in between 0 and 1. So do what we have done before, the polyval. Do you agree? Makes sense? So I would call it xi equals clean space. I want from 0 to 1, I told you, right? If it's 100 observations, I don't need to do anything else. Then what I need to do, guys, is evaluate my function, correct? So polyval, what is my equation? My polynomial is P. What is the data? Xi. So I have already the fit, okay, the data for the fit. Then what I will do is simply plot. What I plot, guys, I will do the following. Just to show you the data. Let's say this, I will show you this is the data. I want the data to appear in bubbles. Then I want XY to do the linear interpolation. And then I want X and Z, and I want perhaps something like that. So what is happening is the following. I'm doing X, Y, O, so that the data is going to appear with the O's. And then when I do simple plot, guys, what MATLAB is doing is simply interpolation. So it's going to appear lines across the dots. And then XY, that is my best fit. Okay, if we run this one here, oh no, it's not X, it's XI. I call it XI, sorry, it's not X here, it should be XI and wait a second. No, it's X and Y, so what is it? 1 second. No, this is, wait a second, so I need what? X. No, so this is okay. This is okay. XY, this is okay. And this one here. Yes, because this XI is the one that goes with C. Yes. Makes sense to you? So XY is okay, XY is okay, but XI is the one that goes with C because I created Z using XY. Correct? And then you
So-
can see, yes.
What does the dash do?
Oh, the dash, you're going to see.
Oh, okay.
Where is my dash here? Well, you don't see, it's this one here. It
Okay, it's
creates,
just
you don't see this, but I don't know why my definition is so good, but indeed it is dash, 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 dash.
so can you pass any character through that?
Oh yeah, you can. You know,
Like a
remember,
dollar sign?
not necessarily all, but help plot. Take a look. So all these characters we can use. Give me 1 second. These ones.
Sorry, what did you type to bring that up?
Help plot.
Oh, help plot. Okay,
Yeah,
cool.
and then you have all. You can do this blue, green, etc. You can do point circles, etc.
Oh, so that means the dash is solid. Okay, cool.
Exactly. So my dash is this one here. Make sense?
Yeah.
And then you can see here the clearly the difference, guys. The orange one is my polyfit. Okay, I'm fitting the curve. And the orange, well, light orange and the deer orange is the interpolation, linear interpolation.
So basically interpolation is connecting the dots.
Yes, yes. You know, you can improve that later. You're gonna see how to improve this stuff.
Okay.
Yes, but it is connecting the dots. Remember when we do quantiles, when we have a quantile between these two positions, then you say, okay, linear interpolation to see what is happening in between. So we always assume that the line is kind of the best, but we have a different technique that works really nice. Okay. Now, can you add to this one here? Add to this one here, guys, a polynomial of degree 1. So assume that you want to put in here the line, how the line fits, and put this in blue with dots. So you need to redo everything from here, right? This is going to be 1. Let's call this P1. I don't know. And then you do everything. You see? And you put the results, the graph, the line in the same graph. Let's say 2 minutes. So what I want is simply to compare the polyfit degree 2 with the linear fit and with the linear interpolation. So you don't need to destroy your graph. I simply want you to add a line here. That is the best fit line. Okay, 1 minute or 2 minutes to recording. Okay, so what I'm doing here now is running my linear regression, right? This is my x, 10x plus 144. And then what I do is, okay, let's create, I have the x1 already, right? xi, I'm okay with this xi. Then what I will do is I will call this C1. It's going to be the polyfit of P1 using xi, correct, guys? And then I want to plot this C1, and I will do a hold on. Why do I use the hold on, guys?
To maintain the same graph.
Yes, to maintain the same graph and to add a new one. If I do hold on, what is going to happen is that we're going to have simply a line. Everything is going to be destroyed except the last one here. But what I'm telling MATLAB is, okay, keep what we have there and add something else. That's a hold on. Okay, and then what do I hold on? So let me go. This is a simple plot. Yeah, I don't need all this stuff. It's xi with c1, and we set a blue. It's a blue star, something like that. Here you go. Make sense, guys? Okay. Now we're gonna do optimizations there. One of the videos you're gonna optimize which is the best degree of the polynomial. But at this point, guys, what I want from you is the following: something that is called overfitting. Got it? So what is overfitting? What you try to say is, you know what? Which one is better, one or two in this graph? Getting the data. Remember the light orange or the blue? Which one do you believe captures better the data?
Light orange.
Light orange.
Right? Exactly. Okay, but I believe you know what? And light orange is n equal 2. So do n equal 10. Create another file so we can delete this one here and simply plot the data, the linear interpolation, and then the n10. So basically your polynomial is degree 10. Or create another figure if you want. So now that you believe that your polynomial that fits the data is polynomial degree 10. And see what happens. Okay, so what I will do is I will call this P2 and 10. Let's call this P2, or let's call P10. Okay. Then I can use the xi is going to be the same. I can do Z10 is going to be a polyad of P10 on X1. Agree with me? And then I can do the plot, the original one here. I will do a figure just to create another one. My plot, blah, 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 xi with z, what's the name of my z? Z10. And we can do this, this is okay, but I want this blue. You see what happens? So when the data tries to feed, sorry, when you have an overfitting, this is what happens. You see, when there is the distance is small, it simply tries to do a very fancy stuff. And of course, this is a catastrophe. So that's why the polynomial optimization, guys, the degree, what is the optimal polynomial is very crucial. Yeah, it's not simply putting any number, just by putting any number. It has a logic. And the logic is basically, in real life, in economics, normally 2 or 3 is the maximum. We don't use more. Got it? 3, for example, is a polynomial degree that we use for the total cost function. Do you remember? In micro, this one that looks like that and it goes like that. polynomial 3. That's all what we have in economics. I haven't seen anything else that is of a higher order. Make sense to everyone? Questions? No? Excellent, guys. So let's close all this
Is
stuff.
there, sorry, is
Oh.
there some method to like figure out the best degree to
Yes,
use?
yes. One of the videos has that.
Okay, cool.
Trevor. It's basically you optimize the distance of the errors.
Okay, got
so
it, yeah.
you have a root mean square error to remember which of the polynomial fits produces the lowest
Minimum.
root mean square error.
Got it. Sweet.
Right? So you know that the logic is very straightforward. Okay, so now I think I gave you, yeah, interpolation. Can we use these ones here? Okay, so let me close this one here. Okay, so let's do a plot here. So these are the hours. What is it? The temperatures in interpolation, and I want to hours, temperatures, and now I want this just to see what we have. So basically, guys, the crosses is real data, and the blue ones, when we what plot does is basically linear interpolation. So these are the linear interpolations of the graph. Make sense? But now we're gonna find the exact values. I want to see the exact value. So I don't know what is this value in between. So let's try to find that. Okay. Everyone is with me? The graphs, do you have that?
Yes, bro.
So the MATLAB command, guys, is interp1. Okay, what do you want to interpolate? I want to interpolate hours, temps, and then at what time, guys? I want to see what should be the temperature at 9.3. At 9.3 of 6 is 920, right? So if I see my graph, what is my hour? At 9:20, around here, my temperature should be 22.9. Make sense to you? Now, what we can do is we can do, of course, a range of values. So instead of 9:30, I can say, okay, I want this to be, what time is it? 3.2, 6.5, 7.1, 9:30, 11, whatever. Okay, so you obtain the interpolated value. So this is the thing that basically the meteorologists used. But they don't use this one. They use something that's called a spline. So let's go back to this one here, and then we simply talk about a spline. And you see the difference, guys, between linear interpolation is 22.9 and a spline is 21.85. So the ones that work with this type of products, they believe that the spline is better. Indeed, when I did some simulations in the past, the spline was much better, was smoother and cleaner. It's not like a robot. It has some curvature, but the curvature has a meaning. Make sense to you? And of course, you can do the same with this one here. You simply add at the end a spline. Or I can do, so for example, imagine 1 increasing by 0.1 to 12. So this is going to be my H. And then we can do my T. Interpolate this in H. I don't want to, it's going to be a lot, right? And then I can do plot. Hours is my X. Temps is my, how do you call it? I will do this, and then I do hours and temps. Hours. I want hours. Okay, so what I want here, I want hours and temps. Hours and temps. Yeah, I can do the cross just to identify the points. And then I will have H and T. H, what is H here? What is my H and T? Okay, so I have my linear interpolation. I have the hours, hours and temps. I need to have temps here. Like crosses, just the points, and that's it. You see the difference between linear interpolation, guys, and the cubic splines? So they try to do a cubic function in between 2 points, following the dynamics of the previous and the post observation. Got it? Looks smoother. In real life, it's more smooth than linear, but you know how to do that now.
So it's always cubic between the 2 points?
Yes, exactly.
Okay.
Exactly that.
Interesting.
Okay, so now let's go into, let me check what I need to show you now. So we have polyfits. Okay, so this is good. So let's do something that is really cool, guys, and allows you to do and check functions in a very simple way. There is a MATLAB function that is called fplot. We're going to use fplot a lot quite soon. So humps is one function that these guys provide just for testing, okay, and for using for different things that we're going to use in a minute. Oh yes, of course, I forgot the comma. Okay, so this is the old version. I always forget. Now should be humps. The new version uses this one here, guys. It's much faster, but produces the same. This add hams. You're going to see in a couple of minutes how the add command works very nicely. And if you see that the time difference in between, it takes time. For one, it takes 1 second. For one, it takes nothing. So this is my hams function, guys. Okay, so fplot, what it does is simply tries to show you functions. For example, let's do another fplot. Let's do fplot. Okay, my variable of interest is x. And let's do, for example, 2 times exponent of minus x times sine of x in the interval 0,8. Someone has an idea about this function, how this function looks like? No idea, right? Yeah, what is this function? I have no idea what this function looks like. But that's the beauty about fplot. So what fplot does, instead of doing the polyval, etc., 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 this one here, this is you cannot express this as a polynomial, right? So it's not x squared, x cubed, not nothing. This is a function that is not a polynomial. So if we have functions that are not polynomials, how do we work with them? Well, fplot is one of them that is going to be helping us to understand what do we have in front of us. Got it? And we're going to see other optimization tools that similar to this one here. Fplot is just a plot. So, so what I have done wrong. Oh, yes, of course. Is this one here. I need to, is this one here. Here you go. Oh, do you get this one here? So it's at parenthesis x. While you do this stuff, let me do another one. I will do x squared. I want this in the interval 0, 3. All right, is x squared minus 2x plus 3. I'm just writing whatever, guys. So this is my function. Agree? Perfect. Beautiful. This f plot is an amazing function, guys. So now finally, I think that we're in a capacity to do some optimization. So let me go home for 1 second. We'll clear all this stuff so I can have a clean part here. Okay, guys. So now what we are going to be doing, let me save this one here. This is class 7. Nothing particular here. Okay, so what we are going to be doing is, for example, these tools are called optimization. Okay, in economics, guys, we always optimize. That's our goal, is try to optimize something, try to maximize something, try to minimize something. Got it? And what we're going to be seeing, guys, is we're going to be using f-min bounded. So this is good for a function of a single equation, single variable, sorry. We're going to use f-min search. This is for multiple variables. And then another function that is also useful that is called f0. So what f0 does, guys, is finds where the function crosses 0. Okay? This one here finds where the function crosses 0. And sometimes it's important. You're going to see why. Okay? One thing that you need to remember, guys, is that all of them are minimum, minimum, minimum. Do you agree? It's trying to find the minimum. But what if I want to find the maximum? Well, remember, guys, that one is the mirror of the other one. So imagine, if I want to find the maximum of these guys, and MATLAB and any other program are Python, everyone uses minimums. They cannot find maximums. So what do? I want the maximum. I don't want
Just
the minimum.
invert it.
Exactly, exactly. So what I will do is I will show you how to do that. We simply create a mirror of this one here. Hopefully it looks similar. Then I find the minimum. And of course, I simply transfer the sign, and then you have the maximum. You agree? So when you say maximizing or minimizing, guys, what you need to try, what you find is first this value, x. And once you find x, you go to f of x to find either the maximum or the minimum. Make sense? That's the way it works. Maximizing or minimizing is simply the reverse image of them. And when you talk about minimizing or maximizing, you try to find x or x1, x2, x3, x4, whatever. Got it? Okay, guys, I gave you the first one here. Can you open the function x example f min bound new, please. Copy this one here, 3 minutes to analyze, and then we go through the process. Okay, let me stop recording. And please remind me to. Okay, so what we try to do here, guys? I have this function here. I think we know this function. Okay, we're going to graph this function soon. And then what I want is, first of all, I want to see how the function looks like in this interval. And then what I try to do is I try to find the minimum, the x that minimizes the values. And I'm using the f-min bounded. Make sense? And what is this fn? Well, fn is defined here. In what interval? Between 2 and 5. So remember, guys, f-min bounded is for one single variable. The function is fx equals x, whatever. Got it? So let's stop here. And let's run this one here. You see, here is my f plot. Do I have a minimum? Yeah, I have a minimum because the function goes down and then goes up again, correct? So we should have a minimum. So where is the minimum? Okay, so let's find the minimum. So the minimum is equal to 3.92. Make sense? So let's take a look here. 3.92, yeah, it's very close to 4. It's close to this part here. So I have found x. What I need to find now is what? Y. Right? So how do I find y? Well, in this case, what I have done is I'm using a function that is called find y min, and the input and the argument is x min. So remember, you can have functions in the same function. So where I define this function is here, guys. Instead of creating an OR file, this big function has an OR function in between the functions. So what MATLAB is going to do is going to import this minimum value of x, put it here, use the equation, replace the values, and give me y. Make sense to everyone? Okay, so let me go.
Okay, but can this function only be called in this document?
Oh, no. You can call it outside also.
How would you write that?
Give me one.
Oh, sorry.
Sorry, guys. Again, your question, Trevor.
So like the M file is called x underscore fm bound.
Oh, this one here. Yeah. Oh, yeah. Just imagine. I take this one here, delete from here, create an M file.
But can I just call this function within this script from a different file? From a different M file?
No.
Okay. Just check.
No. You need to
Okay.
have, yeah, I understand it, but no. If you want to call this y f min, find min, y min for another program, no. By
Got it.
alone,
Okay.
you need to put it in independently, right? I did it just for not creating so many small programs. Then, okay, so if we run to here, take a look to what happens. So my y min equals minus 0.0279. Do you see that? If we see the graph, guys, it's very tricky to really distinguish this value, but it's around 4, and the minimum value of y is 0 minus 0 point something, 0.279. Make sense? Make sense to you guys? So that's the way in which we find minimums. Okay, so let's continue working on this stuff. I'm creating a figure. What is this one here? Okay, I don't know what I'm doing here, but let's take a look to here. Oh, yeah. So I have this function now. So this function here is the 2 times exponent minus x times sine of whatever. And what I want is to find the maximum value now. Correct? But remember, guys, we don't have f max, we have f min. So what we need to do is very straightforward. The image of a function, guys, is a negative of the function. Okay, that's it. So what we do, what is this fn different from this fn? Is simply the negative. Do you see that? And then let's plot this one here. You see, if you compare these two guys, now move. If you put one below the other one, you see they're exactly the same. This is what I was graphing to you. So now I'm working with this one here from the one that is in the lower part. What I will do is I will find X and then I will find Y. That's it. Okay, so X max is going to be, oh yeah, this is another thing that happens and it's very useful. Fn, so I'm in between 0 and 3. And this optim set, guys, display iterations is very useful. Why? Because sometimes you don't arrive to a conclusion. There is no optimal, there is no minimum. And sometimes the functions are very complex. Got it? So you want to see where the problems start happening. Okay, this is basically to determine which initial values you're going to be using. So let's take a look to what happens with this one here. I will stop here. And if you see in here, so it appears that the value of f of x, so what it does is linear, it's simply optimization. And what it tries to minimize the errors. Okay, so these are the rules, golden rules, parabolic. There is a lot of rules for optimization. And then once it's done, it says optimization successful. You know, this is my margin of error, guys. Very small. Make sense to you? So this is what optim set does. Okay, then I find my Y max and then I'm done. So let's try to look what is my Y max. 0.6448. No, what is the other one? So it tells you my X max is at 0.7854 around here. And then my maximum value is equal to 0.6448. Make sense to you guys? Got it? Clear? Excellent. Okay, so now let's go to the other optimization technique. This is more generic. Can you go please open your Word document and open this file, fmin search. Yeah, it's this one here. Copy this one here, guys. 3 minutes to analyze, and then we continue. Let me open this in MATLAB. Yeah. Okay, 3 minutes. Okay, guys. So remember that the X-min search, the F-min search is a generic version of optimizers. Got it? You can have as many variables as you want. And what I'm doing here, guys, this is my function. I'm sorry, my function is somewhere here. This is a function that I have. So it's x squared plus 2.5 sine of y minus c squared times x squared plus y squared. This is any function. I just created any function, right? And what happens is that when you have an F-min search or any other type of search, you need to have starting values. You need to put starting values, okay? In this case, I have selected these ones here. And then what I do is simply very simple. A is gonna capture the values that minimize my function. So F-min search, I need to have a function. What is my function? What is the name of my function? 3var, do you agree? Is this one here. And what 3var needs? It needs starting values, V. And why I need this at is more or less like the F plot, guys. The at, the sign, like the at in the email. It simply tells you, it directs MATLAB to look in a place. So where is gonna MATLAB look for the function? It's gonna look for the function in something that's called the 3var. So what MATLAB is gonna do is it's gonna take the values, the starting values, input them, divide them into pieces. So X equals to the first value, the second value, the third value. And then B is going to be simply replacing the values. And what with F-min search does is simply starts moving the values, moving everything at the same time, trying to find a way in which there is directionally something that goes in the minimum direction. Do you see? Move variables, and it sees that the values are increasing, changes the variables. the values, sorry, and then looks for new values until it feels that it's going down, 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 and then suddenly it's going up again. And so, oh, I found a minimum. Got it? The problem with this type of optimization, guys, where you don't see the functions, is that you don't know if it's a local minimum or if it is a global minimum. Okay, and that's very crucial for you when you do research, guys. And this happened to me. I was creating a new theory in one part of my thesis, guys. Really, I invested at least 2 months doing a theoretical result that was crap. Why? Because imagine, okay, so this is a multivariate version. So imagine this is a univariate version of something that was a huge multivariate version. So what can happen is the following. So you're doing this stuff, doing this stuff. Okay, so obviously, if you see the complete function, what is the minimum? In here, do you agree? However, and how do you find this one here? You need to help the program. The starting values, guys, is simply to help the program. Where do I look? So if you have bad starting values, so what happened with me, guys, is I gave it, without knowing, starting values in this environment. So what the optimizer does is basically moves here, wrong direction, moves here, good direction, good direction, good direction. Okay, it's going up. So basically gave me this value here. Do you agree? And you don't see the graph. So you can believe that this graph, that this point that MATLAB is giving to you, any mathematical optimizer, is the minimum, global minimum. But this is what is called a local minimum. So that's why, guys, when you do your program, what I suggest you is to do, you by theory know more or less what are starting values, but just in case, give, 3, 4, 5 different starting values and test them. And to see if indeed the minimum that you are finding in one is the minimum that finds in everything. Make sense to you? Very simple stuff. You do for loops. Do you agree? So you create a matrix of starting values, a for loop. So the first for loop with the first starting value, second, third, fourth, and then you simply collect all the minimums, and then you see that indeed the minimum, that one of them is the minimum. Make sense to everyone? Make sense? Okay.
Yeah.
So here we go. So and that's all what it does. It simply finds. Give me 1 second. Oh, I have that mouse in here. It simply finds A, but A is going to be the X values, right? I need to find the Y's. So I simply go mean function value. This is a name. I use an eval function. It's another function that I created here with the optimal values of A. So what it does is A is going to be a 3 dimensions. It puts the values of A here, and then it computes the value of C. That is my function. Got it? So you have the values of A, and also you have the function. So this is the minimum value. So this function C is the minimum value that the program has been able to identify. In my graph, is one of the bottoms. I have done this. Oh yeah, it's done already. Oh no, let me run. So let's run this one here. Here we go. So these are the values of A. So this is the value of X. This is the value of X. This one here is the value of Y, and this one here is the value of C. And what is the minimum value of your function? The minimum value of your function is equal to minus 2.5. Make sense, guys? Everyone? Perfect. Okay, so now let's go to the last one. Can you go? Also, I provide you this example to you. Can you please go in? No, I give it no. Yes, the function x f0. 3 minutes. You check, copy, analyze, and run. Okay, run. Understand? Running is where you understand. 3 minutes. Let me stop recording. And then we try to understand what is this doing. So remember that f0 simply tries to find where a function crosses 0. Okay, so that's all what it tries to do. So let's do this. X is going to be f0 of sine at around 3. Do you remember the sine function, guys? How the sine function works? So we have pi, 2 pi, we have 1, and we have -1. So it was like, do you agree? Makes sense? So what we are telling MATLAB is, can you give me the value of the function with crosses 0 around 3? So basically it's should give us something like that, right? Make sense? Where I am. Let's stop here. Yeah, that's good. So we can run 3.14 pi. Make sense? You understand what this program is doing? Okay, now, yeah, at cosinus, so that my function is going to be the cosine function in around 1 and 2. Now, remember that cosine function is a function, what is called a function 1. So the cosine is pi, 2 pi, 1 minus 1. So looks like, oh, wait. It should be 0. It was something like that. Okay. Didn't draw this correctly, but this is something like that. Okay, so around 1 and 2. So we are asking something around this environment here. Y equals 1.57. That is the half of pi, right? Make sense, guys? Perfect. Now I have another function. I have defined a function that is called function f. What is f? Is this one here? Is x cubed minus 2x minus 5. It's a cubic function. This looks very similar to the cost function, total cost function that we use in micro, guys, microeconomics. Okay, so let's try to do that. I'm doing first the plot, the title, before going to the optimization. So let's take a look. You see, do you remember that? The very famous cost function, total cost function that we use in micro. Okay, so what we are trying to do here is, there is a part in which this function crosses 0, yes or not? Yes, 0 should be around here. Correct? This function crosses 0 around this point here. Make sense to everyone, guys? Yep. So if we do that, let's continue. You see the function crosses 0 at around 2.09. Makes sense or not? 2.09 is around here indeed. Crosses 0. Yeah, 209 should be around here. Make sense? Yep. Okay, so before going this stuff, why this crossing 0 is so important, guys? Why do we use this crossing 0 in economics, for example? Do you remember? Let me move this one here. Do you remember the utility function? Utility function looks like that, correct? Right? If this is x, this is going to be the utility of x, assuming that y is constant. And then when I try to find a maximum, so what we try to find is the first derivative equal to 0, correct? But the derivatives are one concept that are crucial in economics. How do we call the derivatives of the utility function? So if I start taking the derivatives at every point of my utility function, how do we call them? Marginal utilities. Remember? Okay, so the marginal utilities starts very high because the slope is high, but it goes like that. Correct? So what happens in micro, guys, if I give you just marginal utilities, can you find the maximum of the function when the function optimizes, is optimized, yes or not?
Yes.
Yes, and when this happens?
Equals 0.
Yes.
When the marginal utility crosses 0. Exactly that. Correct? And now, mathematically, guys, this one here, the marginal utility rule, is much faster and much more efficient than the utility function. This is very simple. It's simply a line when it crosses zero, pack. That's it. That's where you maximize your utility. Make sense? So that's the quantity of X that maximizes your utility. So that's why for this type of problems, we have handy the F0. Makes sense to everyone? Perfect. So let's continue working on this. And then the other one is just to show you how else you can use the optimizer. So sometimes, guys, you have a function, for example, cosine of A times K. K is going to be my variable, but A is going to be a constant. 2 times X, 3 times X, whatever. So how do you tell MATLAB A? You know, part of this function is a constant and part is a variable. Well, I define A in this case. I want to F-plot. Here, what I'm telling is the F-plot using K, use my function. The name of my function is my fun. K and A. But when I tell MATLAB, hey, MATLAB, K is a constant, here is where I define the constant. When I tell MATLAB, use K as a variable, I'm not including A. So this implies that MATLAB is not going to consider A as a variable. A is going to be a constant. And then you simply write whatever you want. Make sense, guys? Okay, let's do up to here and let's see what do we have. So remember, we have a cosine of 2. Basically, the frequency increases by 2. Agree? So the cosine is like that. Now is thinner. And then what I'm telling to you is give me what is the value when this function crosses at around 0.1. And if we continue doing this one here, we just let it go. When K equals 0.7854. 0.78 around this point here. Do you see that? So in this interval around 0.1, K crosses, the function crosses 0 at 0.7858. That is 1/4. Yeah, it's 1/4 of pi. Questions, guys?
Wait, sorry, just to confirm. So we've now defined A as a constant, and then K is being called back with this at line 25.
Yes, and K is going to be moving. K is going to be the one. So technically, brute force, what it means is the following. If you don't know how to optimize, guys, what you're going to be doing is basically taking A is 2, and let's assume K, let's do around 0.1. Okay, let's do 0.1. 2 times 0.1, okay? And then you find a cosine. You know, perhaps you're going to be around here. And then you do 2 times 0.2, and this is going to go down. What you move is K. Do you see that? Now, what happens is K is 0.3, 0.4, 0.5, 0.6, 0.9, until you find a value that makes that makes the function, value of K that makes the function equal 0. That's what MATLAB is doing. Well, the optimizer is doing, but in a smarter way. Do you agree? Because imagine if you do this slightly piece by piece, it will take a year. So it uses the gradient method, for example. If MATLAB knows that the gradient is very steep, it's jumping very fast, so it goes from here to here. But if it sees that the gradient is going smoothly like that, it cannot jump a lot, so it starts jumping less. Make sense to everyone? So that's the basic idea of an optimizer, is how fast you jump from one place to the other place, sometimes based on the gradient. The gradient gives you a lot of information. Make sense to you guys? Okay, so I think with this, you are done with with optimizers, so we can go now into integration. Integrals. Okay, so can we do the following, guys? Let me check if we're gonna integrate and take the integral and differentiate, okay? I think I give you, yeah, can we do this, guys? So delete this one here. I don't know why I put this one here. So let's do first these 3. Just to understand what we're going to be doing. Okay. So let me delete this one here. Move. So I have my function, guys. And remember, what is the integral? It's simply finding an area below a curve. Do you agree? That's all. Now, how do we find an area below a curve, guys? There are a lot of techniques. One of them in MATLAB is called what is called the trap Z, this one here. How the trap Z works. So we can take a look to the trap Z, and I will explain what is a trap Z. So what it's telling to me, guys, that the area below this curve is equal to 25, 94, 74. So what is this technique trap Z using? It uses rectangles. So let me go back here. Oh, so let me say this different. Okay, so I have my function. Let me move this somewhere here. I don't know. I will graph my function like something like that. Okay. So what the trap C does, guys, is it builds rectangles. Okay. When it's steeper, the size of the rectangles, the width of the rectangles is very, very small. Well, I haven't done places that is much flatter. So there, if find surfaces that are flat, the rectangles can be wider. Do you agree? When it's steeper, the rectangles are very small. So that's the way it works. However, you can see when you do this type of technology, guys, it's easy because you're building simply rectangles and then summing all the rectangles. The problem that you have when you do this type of things, guys, is that you always have these small peaks that are outside or too many inside the function. Do you agree? Now, and that's what trap C is doing, guys. Now, why the trap C is used? Because it's fast. When you have very complicated functions that are multidimensional, so it's not area, it's volume, for example, then in that case, trap C gives you a very good approximation of what you're going to try to find. Got it? So this value of 25.94, it is a very good approximation of that. So, of course, we can improve that. If we go, can you go? I think I gave you. Can you go these ones here, guys? What I have done is instead of using 0.17, I'm using 0.07. So I'm giving you more points to analyze. Let's do this in MATLAB and take a look to what happens. You see now? So the thinner the grid, of course, the much better your forecast, your trap C. Okay. However, guys, there is an optimal way of doing this. That is quad. Okay, let's do quad and quad L. Okay, my function is humps. Humps. And I want this to be in -1 and 2. This quad, guys, is the one that is very flexible in terms of determining the width of the rectangle. This is the most efficient one. What is one of the most efficient ones? The most efficient one, guys, is quad L. Okay, you don't see the difference here because my function is beautiful. It's very simple. So trap C is the fastest one because it uses rectangles only. The quadrature is much different, and the quad L, this is an L, this is not a 1. This is the optimal one. Now, when you do simulations, guys, in real life, when you research, if you try to use quad L, it will take a lot of time. It will really take a lot of time and sometimes collapses your system. Okay, so when I learned about this stuff is when I was doing I started always using the quad L. It's the most efficient, blah, blah, blah. I put it in my program because I wanted to find probabilities in a hyperspace. And it took almost a week and then collapsed the system. Got it? And this was a nightmare. It was really a nightmare. So I invested 1 week on nothing. Make sense? So then I discovered this quad L. It was the same stuff. Then I discovered trap C. God appeared to me. 30 minutes, the value was there. Okay, and then you can start, optimizing better ways of doing that. Because the quad L, remember, how do you optimize the quad L to be more precise? Is the thickness of the rectangles. You see that? That's why I show you here. When we have a thickness of 0.17, my quad L was 2191. But just take a look to what I did. 0.07. My quad L, my trap C provides me a very close number to this ones here. Do you see? Make sense to you? Okay, good. So, and this part here is crucial, guys. And I discussed this part with Professor Collins and Professor, the dynamic guy, I always forget his name. Philip.
Yeah, Phil Shaw.
Phil Shaw. Because the people, what they do when they try to take differences, what they do is they take the diff function, like we do it in math, d of x respect to d of y, and they try to find the functions. Okay, that's wrong, guys, because I will show you. It is a catastrophe. First, you need to do the fit. Then, once you have the fit, you take the derivatives of the fit, and then you take the differences. Okay, let's do this. You're gonna understand what I'm talking about, and I will show you that the catastrophe that you create when you don't do that. And where's my this one here? So let's start working on this one here. Okay, can you copy? Yeah, we have done that. So let me explain. These are the values. I'm doing a polyfit N2, so I'm doing a polyfit order 2, and I just want to see the values. Okay, can you take a look to, let's copy all this stuff. We are almost on time, and I want some minutes to talk. So let's go. Yes. Okay, be sure that you are here with me for a minute. This looks like my utility function, guys. The data, the dots that you have here, look like empirical utility function. So you start asking questions to the people, interviewing the people, and you realize that what is the utility that they found when they start consuming more of a product. You agree? And normally this goes up, but then it slowly goes down. Okay, this is a typical utility function. So what I want to find here, guys, is what I was telling to you. I just want to find the function that defines the marginal utility functions. Okay, the marginals. Okay, so what you need to do first is feed the data. That's what is called smooth the data. Okay, so what you need to do first is find that, we don't see this very well, but you have the fitted value. It's a quadratic function. You see the orange dots, orange. You see that? It's very hard to see. Yeah, do you see them? Guys, do you see them? Okay, so
Yes.
let me.
Yes, prof.
Oh, perfect. Okay, so first thing is smooth the function. So you need to find a function that determines the function, the dots, that fits your dots. This is what we have done here. And then you determine your polynomial. So this is the polynomial that fits my data. Got it? Now, what you can do now, guys, is we can use the poly there, because that's the derivative, right? The marginal utility is simply the derivative of function. So we can do PD equals poly there of P. And then how do we do in order to build my function, guys? I have this is the polynomial that represents my marginal utilities. Now, how do I graph them? How do I create a series of them? Well, what I can do is I can create Z equals polyval PD, and my data is called XI. This one here. I will semicolon because I don't want to see the 100 numbers here. I think I give you this also or not. Yeah, this is the one, and we can copy this part here to plot. I need to create this one here, and then I want to plot xi with z, etc. So take a look, guys, to your. Do you see? Okay, when you do dynamics, we're always going to be optimizing. We're always going to be looking for functions based on data. But don't use the data and make the differences. I will show you in a minute. I think you have that. First, smooth the data, then compute the derivatives, and then you have your beautiful marginal function. Okay? And from this marginal function, you can do whatever you want. Your results are going to be very, very meaningful. So what happens if you don't do that? Okay, 1 minute to understand and be sure that you get these values, please, guys. Okay, so take a look to what normally the people do. Okay, so my mathematics, the derivative of y is simply the difference of y divided by the difference of x. Do you agree? Mathematically, this makes sense. So, whoa, no, to be. I'm talking about this one here. Got it? I just take the data and I take the derivative. Then I create xd. See, this is simply my values that I will analyze. And then I simply plot. Can we do this? And take a look at what happens. And this was the main issue. Oh, I delete my previous one. Well, take a look, guys, to your marginal utility. Do you see that? A catastrophe, right? You cannot do analysis with this one. And that was with what Professor Sean was telling to me. So the students were simply collapsing when we're doing I don't remember what dynamic model, but the results were completely crap. And that is because the process is always the same. When you do research, guys, the data gives you an insight of how the function looks like. Got it? So that's why you first need to optimize, need to feed the data. Once you feed the data, there is a best representation of a lot of things that happen in reality. Then you do the derivatives, then you use the marginal analysis for that. Make sense? Okay, perfect. So with that, guys, we stop here in the class, and I want to start talking a little about what comes in the next couple of days. I already discussed something. Questions before moving to something more?
Yeah, I just have a quick question
Yeah, go
for
ahead, Lauren.
your under, so I can't just read what line is, but under evaluate polynomial, so the next line after that.
Polyval, this one?
Yeah, so can you explain, so I get the xi and z where
Yeah.
that comes from. Can you explain where the first xy and then the second xy come from
Yeah,
again?
yes. These are data. Do you agree? X and Y are data.
Yeah, the original
Yes.
ones, but what's the difference between that one and then,
no.
yeah,
No. This one here, what it does is simply, it doesn't, you tell MATLAB, don't do the interpolation. Simply, when you see a point, an observation, just make a round. That's all. When you do X and Y without anything else, you are telling MATLAB, do the interpolation. So if you have
got
2
it,
points,
okay.
do the line. Make sense? And well, this XY is what we have created and use dots as a representation.
Perfect, thank you.
Okay, pleasure. Okay, guys. So now I need to see. Let me write here. I will just write in the order I'm seeing you guys. Lauren. I see Bafana. I see Karina. I see Trevor. Give me 1 second, guys. I want to see the list. I see Siki. Where's my mouse? I see Siki. Oh, I see Babja, and I see Jason. I think that those are all. Oh, Alfredo, of course. Okay, guys. So I have 2, 4, 6, 8. Yeah, this is good. 4 or 3 and 3 and 2. You know what? Perhaps we're gonna do groups of. It's much easier to work with one, right, than working with 3. Okay, so let's do groups of 2. Right? I just simply, as I written, I simply collect. That's it. Or do you have some preferences? Because I want you to work in groups. But Lauren and Bafana, are you okay working together?
I'm good either way, but I chatted with Trevor. We would like to work together. That was going to be my preference.
Okay, so Lauren and Trevor. So you're group 1 then. So Bafana and Karina, you're okay?
Yeah, I
Yes.
don't mind, bro.
Perfect.
Yeah.
So guys, you're group 2. Siki and Babja, are you there, guys?
Yeah, we can work together.
Perfect. So guys, you are group 3. And Jason and Alfredo, are you there?
Yeah.
Okay,
Alfredo
so
says he keeps disconnecting. He texted me.
okay, Jason.
I'll
So
let him know.
perfect. Okay, so you are group number 4. Got it? So now what happens next? So tomorrow, Thursday, what I will do is I will send you symbolic mathematics. Okay? And symbolic mathematics, guys, it is extremely powerful. Because why? What is symbolic mathematics? Do you remember when you solve an equation? What do? You don't put numbers. You just write. You know, the derivative, you write. So that's symbolic mathematics. So you represent your answers by symbols. Got it? And this is extremely useful. Why? Because mathematical models normally first go in mathematics. And once you find your closed form solution normally, then you use numbers. Do you agree? And that's exactly what symbolic mathematics is going to show you the video is kind of long. It's 2 hours, 2 hours and a half, but it gives you a lot of examples, goes in a lot of economic examples that are going to be distributed to you also. So this is the first thing. First thing is to watch and understand. Okay. The second thing is this is by Friday. I will send you at least 10 to 15 programs and files. And I will distribute this in terms of, difficulty for each of the groups. So each group is going to have more or less 2 or 3. No, it's going to be 3 to 4 M files per group. And it's going to have one that is long and a lot small ones. I will give you some definitions of the model. I will give you a lot of ideas, but you can also look around and try to explain that. And on Monday, guys, so what you need to do first half of Monday, you need to explain to the class. So perhaps not all of them, perhaps 1 or 2 of your programs, you need to explain them to the class. So you're going to say, for example, the Bafana and Karina, you have a model that does the campaign model. Got it? So you explain the model. Okay, guys, the logic, you use Paint or something. More or less, what is the logic, how the model works? You need to explain me that in general. And then you go to the MATLAB program, and then you start running to remember the red bullets. Oh, so here I'm getting the data from MATLAB. Here I'm doing this stuff. Here I'm doing this stuff, blah, 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 etc., etc., etc. And that's it. This is the first part on Monday. This is half class. And for the second half, guys, what I will do is I will meet with you, and I will give you a list at the end of I will send this tomorrow with your names. What I want is you're going to have, 10 to 10 minutes, 5 to 10 minutes to talk to me about your idea. If I see that your idea is already brilliant and I can give you some insights, okay, you go. And then I think that we can do separate rooms, right? You're going to help me with that. So you all keep in the same one room, then I will be moving one by one to another room and we chat for a couple of minutes and then you're ready to go. Make sense to that?
I
And
sorry, at the end, I have a question about that. Do you mind if I stay back at the end? Yes. About the
the
model.
the end of when? On Monday, you mean?
Today. Not 5 to 10 minutes. I just have one question.
Yeah, ask because it's good for everyone, Lauren.
Okay, good. So essentially, I was looking over the question and you said any model. Essentially, what I was going to do is not necessarily like cap him or something, but essentially, I was going to do a two-stage least square of using a data set about finding a specific outcome. And I didn't know if that was acceptable. It's essentially going to be
Yeah,
like,
yeah,
or
it will if you do a lot of more things. For example, yeah, the two-stage OLS model is you can create your own model, your own program, and run everything, and you describe your results. But perhaps what you can do is just add F-plots, just add some optimizers, just try to add something more to the program that is not necessarily needed for your program, but shows me that you are using MATLAB.
okay, got it. So
Okay?
that type of model is okay because I found the data set already. So
Yeah.
others just add additional. Okay, good.
Yeah, no, that's okay. That's perfect. Okay. And remember, guys, that for next Monday, not this Monday coming, the next Monday, you need to provide me for sure. Oh, yeah, the homeworks, all of them. So all the homeworks are due Monday. What day is that?
29th.
29th. Thank you, Karina. Okay, so and the homeworks, please, must have the following structure. Okay, so in it cannot be a PDF. I have received from someone a PDF. It's a nightmare. When I try to copy paste into MATLAB, it doesn't work. It changes everything. So I invested too much time. Please, Word. Okay, use Word. Don't LaTeX also, because LaTeX uses a beautiful way of presenting formulas, but I cannot copy. Okay, Word. So you do homework, for example, 1 underscore your name. Okay, please be sure that if you copy your working groups, at least you're using your surname. I have received guys that provide me the surname of your colleagues that was working with you. Change your surname. You need to be sure that you put your name at least. Got it?
If so, I've been sending them sporadically. Do you want me to redo it? Because I think I have
No,
to.
no, 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 no,
Okay.
no,
Okay.
no. Wait. Lauren, yes, for the final delivery, I want everything to be sent together because I have read a couple of yours and Karina also and Trevor, yes. But the thing is that I want to have them because remember, then I have a couple of days to grade everything. So if I have this separate where I don't know who's who, it's going to be a nightmare for me. So if you can send me back everything by
Got
this
it.
Monday.
Okay.
Okay.
Perfect.
Now, if you are using Excel, the same convention. So it's homework 1, username, XLSX. And then, of course, if you're using M files, the same. If you use M files, guys, just do one M file. Question number 1, so you comment that question number 1, question number 2, question number 3. A single file, a single M file in which you simply say homework 1, username. .m. Make sense? That's the way you delivered your homeworks. Now, your project has basically the same structure. You have 1-2 pages maximum, please. Don't do a lot. Describing the model. What is important for me, guys, to understand your model is you need to have formulas. What formulas you're using? Got it? Because what I do is very simple. I go to your idea. If the model, I know the model, I can go directly to MATLAB. But there are some ideas that I have never seen. So I need to read the logic, the mathematics you're using, and how can I map that into your MATLAB code. Got it? And then I can read both. one page, 1 or 2 pages. It's not 1/2. It's 1 or 2 pages. Okay, so you have up to 2 pages. Where's my mouse? No, it's 1 or 2 pages. Okay, and then you have the data you use in the format that is required. Then you have your M files, etc. So the naming conventions for this one here, guys, is final underscore your username. Okay, so .excel.m. Make sense, guys? Don't in the M file, don't name your M file model ISLM. No. It's final username.m. Inside the program, I will see all the things you have done, but don't name the model in the name of the M file, please. Make sense? And that's all. So the homeworks and the projects are going to be due on May 29th. Okay, so we are done with Monday. On Wednesday next week. So here's an open space for you. So you need to tell me by Tuesday, Professor, can we chat? I want to show you my preliminary results. Okay, so if you don't write me anything, I assume that you're doing very well and you don't need help. If you need help, if you want to show me something, just let me know, and then I will tell you, okay, we see you from 5 to 6 to 6:15. Okay, normally there are going to be slots of 15 minutes, but you need to tell me by Tuesday. Let's say Tuesday around noon, you need to be telling me, I need to meet you, I want to show you something. And if there is no one appears, we are ready. Make sense? I will send you a lot of things, guys, that are coming, and you're going to be more than proficient. And you're going to see that by doing this project, by doing the homework, and doing this analysis for Monday, presenting to your class, you're going to learn a lot. Okay? You have a lot of learning now. I'm pretty sure, guys. I'm pretty sure you can do a lot of very good programs now. Okay, guys? No questions? So we stop here, and then we see you.
Professor.
Yeah, go ahead, Karina.
For Monday, you said that we had to have like a proposal ready. Did you want us to send that to you as well, or just for ourselves?
No. For Monday is not the proposal. For Monday is not necessarily. Well, if you can do it, more than happy. No, sorry. Yeah, I know. I was missing that. Thank you very much, Karina. Thank you very much. Because you know what I need for Wednesday is a formal proposal. Yeah, I was missing something. So Monday is just discussion. If you come to me with an idea, I tell you, you know what, this looks too simple. Can you add some stuff or change your model? So this is Monday. Okay. Wednesday is when you need to send me your formal proposal. You know, it should be almost the 1 or 2 pages that you're going to be working with. And then if you have questions on Wednesday, again, we meet, or otherwise we simply move forward.
Okay, so that proposal should have like the mathematics and everything already. Okay.
Exactly.
Okay.
So don't invest a lot of time for Monday, because Monday I can tell you, change it, right? But Wednesday you need to have it. It's very strange, guys, that I changed that proposal, because what I want is you to do something that you really can apply for a work, or can apply for future research or analysis, whatever you're doing, do it. And also crazy ideas. Remember that I told you the racing, the horse racing idea. Wow, it was very interesting, because he was using statistics, he was using probabilities, and he was using, of course, MATLAB. Got it? Make sense? Okay, guys. So we stop here, and we see you on Wednesday. Wednesday, on Monday. Got it? I will send all the material, etc.
Thank you.
See you guys. Take care.
Night.
Have a good night. Bye-bye.
Sorry, Professor.
Oh, yeah, Siki, go ahead.
Sorry, I have a question for
Yes.
the homework. I mean, if I have already copied and pasted my command in the Word file, do I still need to send you an M file?
You know what? I prefer that, Siki.
Or
Yes, please. It's just create the M file. So for me, it's easier, because what happens is, remember, I have 2 days to grade everything. So for me, it's much easier to open MATLAB and open your M file and then see what's going on. Then copy from Word to M file. It will take more time. Okay? Perfect, Siki.
Thank Thank you
See
very
you later.
much.
Good night. Bye bye.